So this is from Math 2318 students. We're getting some more topics from sections 5.1 and 5.2 that we need to make sure you understand and can prove some of them and use, certainly all of them. Before we go on to talk about similarity and diagonalization of matrices, which is what we're going to be doing in section 5.3. Okay, so we have 6 topics to discuss. All right, so here basically is the list of them. All right, so the first one is that eigenvalues of a triangular matrix are its diagonal entries. So for example, if A is a lower triangular or diagonal matrix, that means above the diagonal are all zeros, right? So when you're trying to find eigenvalues, you solve the characteristic equation that the determinant of A minus lambda I is equal to 0. That's what that looks like if it's a lower triangular or a diagonal. A diagonal would also have all these elements below be equal to 0. But if we expand along that first row, then we have -1, the determinant here, -1 raised to the 1 plus 1, right, times A minus lambda, that would be in that first spot there, times the minor, the determinant of the matrix that would exclude that first row in that first column. Okay, plus 0 times everything else, plus 0 plus 0. That's expanding along that first row. And so all this equals 0 is the first equation, right? Okay, so that's what we're going to call start equation, where the determinant of the minor itself looks like a sum of -1 raised to, well, it's always going to be I plus I, right? Because we're, if you exclude the first row and first column, now we're looking at A22 minus lambda. So you need -1 raised to that 2 plus 2 power. Well, this 2 plus I is equal to 2I, right? So -1 raised to -1 raised to the second power raised to some other power. That's the same thing as -1 squared, which is just 1 raised to the I power. That's always going to be equal to 1. So those are just always going to disappear and just equal to 1. And we're left with AII minus lambda, starting with A22 times minus lambda times its determinant of its minor. Okay, so excluding the second row and the second column. And so as we proceed, we end up getting, there's only a finite number of steps until we get to the start equation is equivalent to the following. A11 minus lambda times A22 minus lambda times A33 minus lambda, all the way down to ANN minus lambda. All that is equal to 0, that product of those factors. Well, that's an nth degree polynomial in lambda. And from algebra, we know that has at most n roots. We know that n of them are A11, A22 through ANN, so there can't be any more. So therefore, can you see this at the bottom? Therefore, oh dear, that's going really well. The eigenvalues of A are exactly those diagonal elements of A, A11, A22. And a way of writing that, the diagonal elements of a matrix, is to use that notation. Okay, so that's our first observation done, right? Now, the second one, I'm going to call lemma 13 for future reference. That goes like this. It says lambda equal to 0 for A. Now I'm just going to start to use this kind of shortcut notation. If I say lambda equal to something for A, I mean that value is if that is an eigenvalue for A. Okay? So lambda equal to 0 for A is going to turn out to be true if and only if A is non-invertible. Let's look at that proof right here. see the whole thing there? There. Okay. So, well, the claim, let's look at it in the forward direction. If lambda equal to 0 is an eigenvalue for A, the claim is that therefore A is non-invertible. Okay, so here's a proof in that direction. If lambda equal to 0 is an eigenvalue for A, that means AX is equal to 0x. Sorry, that equation, excuse me, has a non-zero solution, X. Well, any field element times a vector is the same thing as the zero vector. So, and glare again. Dear, let's see. Too many chords. Let me move that. Does that help? Or does this help? Less glare altogether over there. Come over here. Right, okay. So if lambda equal to 0 is an eigenvalue for A, then we have a non-zero solution to this equation, which is a non-zero solution to that equation, which means the null space of A is non-trivial. It's not just the zero vector. By the invertible matrix theorem, okay, so that's that thing that has been spanning many pages. We have been building up. Many of our lemmas 1 through 11 were involved in that. Your book likes to refer to this as IMT at this point, and so we will as well. So by the invertible matrix theorem, since the null space is non-trivial, the matrix A is non-invertible. Okay, so now remember that if you have an implication, P implies Q, okay? If that's an implication, then its converse is not necessarily true. The converse is Q implies P. So we have to prove that here. So the converse of this would be if A is non-invertible, then lambda equal to 0 is an eigenvalue. All right. So the proof going in that opposite direction, second half of this claim, A non-invertible gives you that the rank of A is less than n. All right, well that implies the nullity is greater than 0. You of course remember the definition of rank, right, and nullity. We discussed those before. You do need to keep up on those, so look that back up if you don't know what those are. That implies the null space of A. If the nullity is greater than 0, that means there's some non-zero vectors running around in the null space of A. So it contains the 0 vector, but not equal to just the space, that is the set containing just the 0 vector. So there is a non-zero vector for which AX is equal to 0, and therefore AX equal to X of naught, this solution we found here, is equal to the 0 from the field times X naught, because that is equal to that, which you've had from, I think, week 2 in this class. So therefore, we have shown by this statement that X naught is an eigenvector for A with lambda equal to 0 as an eigenvalue. And so 0 is an eigenvalue for A. All right. What else do we need to show here? Let's see if that shows up. We're on number 3. Okay. Which I'm calling lemma 14. If we're talking about A, an invertible matrix having an eigenvalue, then the reciprocal, remember that, is the same thing as this, right, in any field. 1 over lambda is an eigenvalue for A inverse. Again, I'm using my shorthand notation. By this, I'm just saying this is an eigenvalue for that matrix. All right, so let's talk about that. This is one of these really cute and short type of things you should be able to prove yourself. Okay, really good final exam question, if I might say so myself. So let's see, number 3 is what we're working on here. Okay, this one here. All right, also known as a lemma 14 for us now. Okay, so you have an invertible matrix with any old eigenvalue. Its reciprocal is going to be an eigenvalue for A inverse. So the proof of that, the statement's right there, so I don't need to write that. Okay, so lambda for A implies there exists a vector x not equal to 0 such that ax is equal to lambda x, right? No glare? Okay. Is there glare there? I can't quite tell, so I better move it. Okay. Well, so we have this equation here, but A invertible implies there's a inverse running around, right? So we can multiply both sides of this by A inverse. Now, isn't that nice? Now we have, this is just the identity on x. And over on this side, that's a constant that can come out front. We can write like that. And so we're left with x is equal to lambda times A inverse times x. Okay. Now, of course, our goal is to get to a statement that looks like here, that we're trying to show that 1 over lambda is an eigenvalue for A inverse. So the next to last statement we want to look like is this, right? So how do we get from here to there? Well, first we could just flop this equation over, right? So far we have A inverse x with a lambda out front is equal to x. A little space there, right? So all we need to do is divide both sides by lambda. But is lambda non-zero? Well, of course. So note, lambda cannot be equal to 0. Why? Can you stop the video and answer that question yourself? That would be a good idea. Lambda cannot be equal to 0 because of lemma 13, right? Lemma 13 said if lambda is equal to 0, lambda is equal to 0 if and only if A is non-invertible. But here, in this lemma 14, we start by saying A is invertible. So lambda is not equal to 0 since A invertible implies lambda is not equal to 0 by lemma 13. Right. So right in here is where you need to say that. And so we can divide both sides by lambda. And so we have this is implied since lambda does not equal to 0. And that gives us that 1 over lambda is for A inverse and is an eigenvalue for A inverse. Isn't that nice? You should be able to do that, work that through yourself. Oh, sorry, didn't get rid of the rest of that other proof, right? That was from before. Okay, so that's number 3 done as well as 2. We got this, all these checked off. Number 4, if lambda is an eigenvalue for A, that implies that lambda is also an eigenvalue for A transpose. And I think I should put that on the next video. All right, So my next video is going to have these items on it. Okay.